Welcome back, chemistry fans. Sorry about the naked shoulders. We are tonight going to talk about the covalent bond nomenclature. Let's get into it. Here it is. So binary covalent bonds. What that means is because it's binary, it has some similarities to what we've already learned about in that we had binary ionic bonds. Now we're talking about something called covalent. Now, what this means is it's a completely different method of bonding. Whenever we had ionic bonding, we had a desire for an octet rule through exchange of electrons. One atom lost an electron, one atom gained an electron. But this time we're going to have exclusively sharing of the electrons. And it's going to make a lot of compounds that you're familiar with, such as water, such as ammonia, and some of our diatomic elements that we've already discussed. So what you'll see in this image here, images, is that with the covalent bonds, there is a sharing of the electrons. Both atoms contribute electrons, and both of them need them to satisfy their stable octet. Whereas whenever we had our ionic bond before, what happened is one of the atoms gave away its electron to create a stable octet. And what it revealed underneath when it lost the one electron was a stable octet. But with the we must count, both of them must count those same electrons that are being shared in between them. So this is the new dynamic that is called covalent bonding. So again, here is another dynamic with it. If the atoms exist on their own and they don't have a stable octet, they will come together, share those same electrons to form their stable octet that they need. Whenever we see this as an orbital notation, you will notice that hydrogen has one valence electron, where the fluorine has 7 valence electrons. So hydrogen could give its one electron, but then it would need still an electron. So we have to represent this by circling both of them, showing that those electrons are going to be in both places at the same time. So there creates a single bond. Well, if we have the fluorines by themselves, it's the same scenario as it was with the hydrogen. They both need one valence electron. I can't give one and take one because that would leave one of them deficient. Then they would have to go and rob it from somewhere else. So they figured out a way to do this, and it is with sharing. Now, one of the key features of this, you will always notice they're always nonmetals, always nonmetals. So here we have oxygen. Now, oxygen's needed 2 electrons. So they have adapted and they said, well, we can share 2. And you wouldn't have noticed that the way that they shared it unless you had thought about Hund's rule, the way that we have to fill out these sublevels with 1 in each box, and then you come back and pair them. You'll notice that you have 2 lone electrons. That's where the pairing goes. And so this makes a double bond. And we can also do the same with nitrogen. We could have a triple bond, but we can't have quadruple bonds. Now, I already alluded to the fact that there is going to be some similarities in the way in which these bonds, these compounds, have names. Because they are binary, they are going to have the suffix IDE. But what is new about this is that we have to put prefixes on each of the elements to determine, to tell the reader how many atoms there are. Because there is no exchange of electrons, there is no charges going on, because both elements are non-metals on the right side. Both elements have the same charge, so there can't be a balancing of the charges. So instead, we have to tell people what the number of atoms are. In this case, we're going to use prefixes that have numerical values. And so here's your list. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, octa is 8, 9 is nona, and 10 is deca. Now, one of the things you will notice, this is not what you expect. In geometry, we would have called that quad, but in chemistry, it will be tetra. And the 7 would be septa. In geometry, it is hepta in chemistry. So get used to those 2 changes. All right. Now, as far as the names of these, it is quite simple. All we have to do is make certain that we are using the suffix IDE as we go across on these. So we will put a prefix for the element, P, hexa, and we would put the prefix tetra for the oxygen. Now, I don't use any suffix for the first element. So it's just hexaphosphorus tetra oxide. Now, if the element begins with a vowel, many times you will notice they will cut off the last vowel of the prefix. But if you put them both in, I will never count you wrong. So tetroxide or tetraoxide are both correct in my book. All right, next we have 2 for the fluorine. So that's difluorine. We have 5, which is penta for the selenide. So this is fluorine, and pentaselenide, IDE. Now everyone knows this one. This one is easy. Carbon dioxide. Now, one of the things you should notice about that is the fact that we didn't put a mono in front. Now you could, and I would never count you wrong for that one, but in the idea of chemistry, they have said that that is redundant. It is not necessary. But then they counter that because if we have CO, you must put a prefix. So it'd be carbon monoxide or monooxide. So I think the fail-safe is just put prefixes on everything. Don't worry about when they get cut off. Don't worry about if you have to cut off any vowels or anything. Just include everything and you will never go wrong. And I will always count you right. Now, this last one is a trick to see if you recognize what's going on. Calcium is a metal. Therefore, there are no prefixes. Again, the scenario that we're falling into, that we're probably without practice going to fall into, is you're going to want to put Roman numerals on everything. And now you're going to want to put prefixes on everything. You have to practice and know when to use the prefixes or whenever we have 2 nonmetals. If the first element starts with a transition, then we have to use Roman numerals. If it doesn't, then we're just straightforward naming. And if there are more than 2 elements, it has a polyatomic ion. So here we have our carbon monoxide that I alluded to earlier. And then phosphorus is a di and chlorine is a deca. Here, you want to reduce that, don't you? You do not, because there is no charges. The reason why we reduced them before is because they were ionic and we were trying to get them to their lowest balanced charge. Well, that's not what is happening here. This is already a sharing of electrons. It is nothing to do with the ions, so we do not reduce it. Same thing for the next one. Dinitrogen tetraoxide. Do not reduce it. Just simply take the prefix and insert the number of atoms. This is everything that I wish to share with you about covalent compounds. Thank you so much. Good night.